Prove that any two elements of A and B in a Euclidean domain R have a greatest common divisor D. Also prove that D equals to ra plus sb for some R and S belongs to R. Proof: let A equals to ra plus sb such that R and S belongs to R. We shall show that A is an ideal of R. Let X belongs to R1A plus S1B and Y equals to R2A and S2B be any two elements of A, then R1, S1, R2, S2 belongs to R. We have X minus Y equals to R1A plus S1B minus R2A plus S2B equals to R1 minus R2 into A plus S1 minus S2 into B belongs to A. Since R1 minus R2 and S1 minus S2 are both elements of R, also if R is an element of R, then XR equals to RX equals to R into R1A plus S1B equals to R1 into A plus RS1 into B belongs to A, because R1 and RS1 are both elements of R. Therefore A is an ideal of R. Since Euclidean domain is an principal ideal of domain, A will be generated by sum of the elements of, say, D equals to A equals to D. We claim that D is equal to greatest common divisor of A and B. Now D belongs to A, which implies D equals to XA plus YB for some XY belongs to R. Again, since A equals to 1 into A plus 0 into B belongs to A, B equals to 0 into A plus 1 into B belongs to A, because B being a Euclidean domain of unity. So small a belongs to capital A and A equals to D, which implies A equals to ND for some N belongs to R, B belongs to A. So A equals to D, which implies B equals to MD for some M belongs to R, which implies D divides A and D divides B. Again, if C divides A and C divides B, then C divides XA and C divides YB, which implies C divides XA plus YB, which implies C divides D, which shows that D is a greatest common divisor of A and B.